This is clip 2 of notes for 3.1, transformations of exponential functions. So our parent function for this function is always the base and the exponent of x. So it's 2 to the x. All of these other things, the 2 in front, that's our value for a. The plus 1 in the exponent is our value for h. And the minus 3 at the end is our value for k. So we're asked to describe the transformation and do a quick sketch of both functions. So 2 to the x, that's an easy enough graph. 2 to the 0 is 1, 2 to the 2 is 2, 2 to the 3, 2 to the first is 2, 2 squared is 4, and 2 to the third is 8, where we have 1, 2, 3, 4, 5, 6, 7, 8. And then 1/2, 1/4, 1/8, and so on, each reducing by half. So there's the parent function f of x. We can get our points, ordered pairs on the table for t of x, but the most critical part for this right now is describing the transformation. Since a is 2, there is going to be a vertical stretch of multiplier 2. Since k is -3, remember those are the things that affect the vertical distance on the graph. Since k is -3, there will be a shift down 3 units. And lastly, since h, and I wrote that in a totally different color, I'm not sure why I switched the colors for a and h is, it's looking like +1 in the equation anyhow. So we have to do the opposite. If it's +1, normally we think, oh, that's to the right. Well, counterintuitive tells us that it's actually a shift left, or translation of left 1 unit. So all of these heights are going to be multiplied by 2, shifted down 3 units, and then shifted left 1 unit. So this would have been 4, and then down 1, 2, 3, and then left a unit. This would have been 2, and then down 1, 2, 3, and left a unit. This would be shifted up to 8, then down 1, 2, 3, and left a unit. I can do this for all of those points that exact way, or I could quickly get a sketch in the graph. 2 to the x plus 1, and then -3 at the end. Go to my table, plot some points like -2, -1, 0, 1, 2, 3. Let me make sure I put that in the calculator correctly, and I did. So -2 is -2. -1 is -1, 0 is 1 like we have, 1 is 1, 2, 3, 4, 5 like we have, and so on. But it's going to approach -3 as its horizontal asymptote, and I should draw those asymptotes in as a dashed line for these functions. So there's a nice brief sketch. I can show my table, or I can follow these operations to get the sketch of the graph. That's the graph of t of x. For my next one, the parent function of f of x is 1/2 to the power of x. 1/2 to the 0 power is 1, 1/2 to the power of 1 is 1/2, squared is 1/4, cubed is 1/8. The negative first is 2, to the negative third is, to the negative second is 4, to the negative third is 8. So there is f of x. It is exponential decay because it's decreasing exponentially, and then exponentially approaching this horizontal asymptote at y equals 0. But this function f of x, well, I did f of x, but this function, the new function, we have a -1 in the exponent. Since h is -1, this means that it is a shift of right 1 unit. And since k is -2, that's a shift down 2 units. So every point on our graph, I'm going to move right 1 and down 2. Right 1 and down 2, 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 2, and you get the idea that it's going to now be a little steeper, and it's approaching now, instead of the horizontal asymptote at y equals 0, it's now at y equals -2. I should have come up with a different name for my parent function. They can't both be f of x. In the next problem, The base that's being raised to a power is 4. So f of x is 4 to the x. 4 to the 0 is 1. 4 to the 1 is 1, 2, 3, 4. 4 to the 4th is 16. So really I should probably be rescaling my graph. 4 to the negative first is 1/4 and 1/8 and so on. Still a horizontal asymptote at y equals 0. This is going to shoot up very steep. Now, I'm most concerned about you describing the transformations. A is 2. This means that there will be a vertical stretch of 2. Every point will be twice as high as it was on the previous graph. Also affecting the height of the graph is that k is negative 3, shifting everything down 3 units, including 1, 2, 3, the horizontal asymptote being shifted down 3 units. And lastly, we have a value of b being 2. B and h are counterintuitive. Instead of being every x being multiplied by 2, the x's will be 1/2, so we have a horizontal compression of 1/2. So the x's are half of where they were before. So instead of 1, it's here. And then it would have been up here, but now it's a vertical stretch of 2, so it's at 8, but then it's shifted down 5, 7, 6, 5. Or shifted down 3, It may be easier for this one in particular to just grab a graphing calculator, 4 to the 2x minus 3, and get a table of values. So for negative 2, I have negative 2.992. Negative 1, negative 2.8. 0 is negative 1. 1 is 29. It's not even going to fit on this graph. I should have scaled my graph very, very differently. It's extremely steep because of that multiplier of 2. But we were able to describe the transformations, which was the most critical point to this exercise. The last part of 3.1 day 1 is dealing with exponential functions that have a natural base. Natural base exponential function is an exponential function in the form of f of x equals e to the x. What is e, you ask? E is a naturally occurring number, the natural base, and it is represented by the irrational number that it stands for. The irrational number's decimal approximation is roughly 2.7182812. Okay, you get the idea. There's the numbers right there. This is usually a great number in population growth models. Not that it's solely excluded to this base. We have other bases depending on the problem. But in natural real-world problems, this is usually the base. That's actually how they found the number. So let's take a look. We have example 3 modified. So we have e to the 3x. Well, e to the x is the parent function, and that's already graphed for you. You can see that right there. E to the power of 0 is 1. Anything to a power of 0 is 1. And then we have the domain. The domain for, well, let's look at the 3 to the x. The 3 to the x I'm going to highlight in red. It's much steeper, but it has the same horizontal asymptote because there was no shift down. So there is a horizontal asymptote at y equals 0. There is no x-intercept. There is a y-intercept at 0, 1. That's the y-intercept. The range for this function is that it will never be 0, but it will go up infinitely. The domain for this is all real numbers. It goes left infinitely, and as it's shooting up really fast, it's also shooting as we go to the right infinitely. The extrema, there are none, because there's no max or min values. If we put a person here, as they walk from left to right, they'd be going up the entire time across the entire domain of this exponential function. And for our end behavior, the limit on f of x as we go to the left. Well, as we go to the left, we're getting closer to this horizontal asymptote, so the limit is 0. But as we go to the right, it doesn't approach the asymptote. It shoots up very fast and increases infinitely. So there is the end behavior for that first problem. The graphs of the next exponential function with base e are given to you. You know that this is a shift down of 1. We see that, where here was the y-intercept, now it's down 1. We also see the opposite, so negative b is a reflection across the y-axis. Where a point was here, it's now over here. And then it was shifted down from there. So our domain for this function that I have right here, not the original parent function, but this function right here, has a new horizontal asymptote that's down 1 unit. Y equals -1. That's going to affect our end behavior as we go to the right. So the limit on f of x as we go to the right is -1. But the limit on f of x as we go to the left, there is no limit. It shoots up infinitely. Now, as we go from left to right, here's my person. They're going down infinitely, even incrementally over here. So this is decreasing across the entire domain. Again, the domain is -infinity to positive infinity for all exponential functions. The range for this one goes up infinitely, but as we come down, it approaches -1 and never reaches it. So I will not use a bracket, I'll use a parenthesis. The x-intercept of this one would have been 0, 1, but because it was shifted down a unit, is 0, 0. It's actually an x-intercept and the y-intercept together. And of course, because there are no max and mins, there are no extrema. In our next function, I'm going to describe what happened to the parent function again. I have a 2 multiplier in front, that's a, so there was a vertical stretch of 2. We're seeing that with this function right here, it's far steeper than the parent function f of x equals e to the x. There was no shift down, so our horizontal asymptote is once again y equals 0, which means our end behavior as we go to the left this time, since it didn't reflect, as we go to the left, f of x has a limit of 0. It'll approach 0, the output will. And the limit on f of x as we go to the right, well, there is no limit. It shoots up infinitely. Our domain for this function, it goes left forever, right forever, without any interruptions like holes or vertical asymptotes. So it's -infinity to positive infinity. The range will shoot up infinitely, but not down infinitely. It's limited by 0. It approaches it, doesn't equal it, so we have a parenthesis. Intercepts, we have none. We do have a y-intercept though, no x-intercepts, but y-intercept at 0, 1. Extrema, there are none. That's not like a polynomial function. And as we walk from left to right, our person's going to be walking uphill very steeply, might be climbing the mountain there, for the entire domain. So as they're like walking way, way out here, it's nice and flat, and then they're like, oh, I hit a wall, I have to start climbing up. That answers all of those questions. To evaluate a function, we would simply put values of x in, which we did on our graphing calculator when we were trying to find certain values to plot on the graph. So, can you evaluate, analyze, can you describe the transformation that's taking place when there's a multiplier of a or of b in the exponent, or it's shifting left or right or up or down? Can you graph the exponential function, which for you can make a table in your graphing calculator, or you could follow, as we did over here, these transformations. Just double check it with your graphing calculator. This concludes the video notes for 3.1 day 1. Hopefully, after, maybe not right away, but after you've done a little bit of practice and exploration with this, you can circle yes as an answer to that first learning target. Have a great day.